Oh, so now that's good. You have made two screens.
So this
Screen two,
this one.
and then which one is your remote desktop?
This is like
But right now, when you will share this one. So might be when you do ask them what they can see, they
yeah.
can enter the change message. So, yeah.
Yeah.
So I think this one will take to the full screen. This is I think this one. Now.
So, and then I don't know why to mute and those things.
Okay, so might be press this one down there. This one. No, the other one.
This one is this window.
Yeah.
It will be fine.
No, I don't know how it became smaller. There must be somewhere that it says full screen. Okay, because we are sharing.
Yeah, now how to stop sharing? Okay, stop here.
Yeah, but let's. Here, that's why. So yeah, so once you stop, you can have, but right now you don't need it. So if you want to share, you can start then. So let's say do share and this one.
Yeah.
And
Okay.
yeah,
Then it becomes this.
yeah, but where you check on them. Earlier you did the check.
It goes out, so then
You do this.
This one's for it. Then press
And
this
check.
one.
Yeah. So now you can start and let's see.
That is the struggle.
Just a good afternoon, everyone. Let's start the second module.
Hello everyone. Good afternoon. Let's start.
Keep checking what.
Yeah. Let's start the second part of the module. Can you please let me know if you can see my screen and the screen that I shared? 10 again.
Prashant, everything is good. We are able to hear you. We can see the slide.
Okay, thank you very much. Okay, so as I was saying that for this part of this module, hands-on, we will be investigating this model TANOGAN, time series anomaly detection with generative adversarial neural network. So yeah, so if you need the code for this one, we already shared the code, and also the code is available on GitHub, and the paper is available online as well. If you need a copy, I think you can access through archive. So it is available on archive. In case if you need, you can let me know. I can send you a copy. And if you use the paper or the code, you can cite it through this citation. Okay, so as we saw that to use a GAN module to detect anomalies, we need to first model the general behavior of a data set. And then if you know the general behavior, then when a new point comes in, we can check that new point against that general behavior. If the new point is significantly different or deviate from the general behavior, then we can flag that one as a anomaly point. So for this model, what we are going to use is we are going to use a LSTM module for our both our generator and description. The reason is the LSTM kind of models, they can handle the time dependency. In other words, they can represent the sequential data. So if something happens sequentially, then LSTM is a good model to represent that kind of data. That's why we are going to use LSTM. So when we are going to when we did experiments, when we were writing during the publication of this paper, we saw that if you use the similar kind of model architecture for your generator and discriminator, it doesn't work well. So we tested with different models, model architecture, and so on. What we saw that the discriminator model should be bigger in terms of number of parameters, and the generator model should be bigger in terms of parameter, and then the discriminator should be smaller or shallow. So what we did is, in the generator part, we used, based on actually experimental result, we used 3 layers of LSTM, stacked LSTM for the generator, and then only one LSTM layer for the discriminator part, to make the discriminator shallow and then generator part deep. Another thing is, we observed that when you stack the layers for the generator, your earlier layer should be smaller number of neurons. In other words, the hidden representation should be smaller. The dimension should be smaller than the later layers. So what we did is we progressively increased the number of hidden states. So what we saw that we used the first hidden layer, or LSTM, was 32 hidden state, and that's 64 and 128 hidden units. So these 3 stacked layers for the generator, and for the discriminator, we used only one LSTM layer with 100 hidden units. Okay, so that's what we are going to use. So from the figure, you can see our real sample is real time series data. Right, so because the real sample or real time series data continues for a long time, say maybe you have 1 million data points, or maybe several thousands data points, or maybe several hundred data points. It depends on your data set. So your model cannot capture the whole data points at a time. Right? This is one point. Another point is, if you give the whole signal, whole the data set once, then the model doesn't have enough capacity to capture everything together. So rather, what we do is we split the time series into smaller pieces through something called sliding window. So a window slides over the time series data because it is sequential. So you can slide over a window, and then anything inside the window will become one segment in the time series data, right? So you slide through that window, and you split your time series data into many smaller subset or smaller chunks. So that becomes each slice will become one instance to train our model, right? So that is our real instances. And then for the generator part, the generator will take a random noise from the latent space Z. And then based on that one, it will make a fake time series data. So it will try to mimic the real one, right? And the discriminator, we have this switch here. You can see this switch can connect sometimes the real data, sometimes the fake data. So this discriminator needs to say whether it is real or fake, right? Is D correct? So based on this correctness or condition or the probability, you back propagate. So you back, or in other words, you get feedback for the discriminator. If the classification is correct, the discriminator is good, otherwise we penalize. For the generator part, we do the opposite. If the discriminator is correct, we penalize the generator. If the discriminator is incorrect, we say, okay, generator is good, right? So that goes on and on and on. So that's how we train it to learn the general distribution. So this generator will try to closely follow the real segments, right? Okay. Now for the detection part, once the training is done, you can see what we do is we ask the generator, right, to generate a sample. But how do we ask it? First, given a sample, we map that to this latent space. I will explain more about how to map it to latent space, right? And then it will generate a sample, and then we'll check if this sample is similar to the real sample we gave. If it is similar, then fine. Otherwise, we will have a threshold. Based on that threshold, we will detect the anomalies. So this is where I'm trying to explain what is happening in the generator part. Sorry, in the training part, like how to learn the general distribution, right? Okay, so for the optimization part, you can see both of our generator and discriminator, both of them are trained with stochastic gradient descent using, and then but this stochastic gradient descent we use through Adam optimizer, so which gives us the flexible or like adaptive learning rate. Here we can see the loss function. So as I said, D and Z, they play in an adversarial game or minimax game with the value function V of GD. So this function takes G and D and try to optimize this. So this value function, we can describe it this way. Let me use the pointer. Right. So what it does is this function, it tries to, so given this function, this whole function, for the generator part, it tries to minimize this function, right? So it tries to minimize. And then for the discriminator part, it tries to maximize this function. So this function, one player, G, is trying to minimize, another player is trying to maximize this one. That's why it is called minimax game. So here, if you look closely in this function, this x is your real data. So this x is, you can say x is sampled from your real data. So it is a real sample. It goes to your discriminator, and then it says, well, what is the probability that it is a real data? Now, if this probability is high, that is good. So your discriminator tries to increase this probability. It tries to increase this part, right? It is real. For the fake data, so you sample it from this part, right? This fake data, in other words, G distribution of Z. That means it is coming from the random space and then the generator, and then you get the sample, right? So when you sample a fake sample or fake instance, then for this one, your generator gives you the fake sample, and then your discriminator tells it whether it is what is the probability it is a real data, right? But if you take 1 minus probability of being real, that will give you what is the probability that it is fake, right? So what do you want? That this fake probability, that 1 minus this part, this whole part, you want to maximize this part as well. So your discriminator tries to maximize this part and this part. And you know that we take the log here to make it, because log is monotonous, and then log has some property that is good for binary classification, right? Because log looks like something this, right? So this part will exponentially penalize if it makes a mistake here. That's why we use log. So that have nice property that is good for binary classification. That's why we take the log. That's why you will always see that the cross entropy and those kind of things are based on log, right? Okay, and then so you can see that your discriminator will increase it or will try to maximize this probability. On the other hand, your generator, now if you see the generator part, this part is telling that it is a fake data. So your generator wants this one go down, right? So you minimize this part. And for this part, because generator is not generating real data, for the generator, this part is just 0, right? This part is 0. So your generator will only minimize this probability part, right? This part, only this part. Now you can see that your generator and discriminator working in a minimax game where the generator try to minimize this score and the discriminator try to maximize this score. So now you train the model for many times, and then after that, when the training is completed, what you do is now you need to like see what is the generated behavior for your real data. So to do that, you map this sample, the real sample. So this vector is coming from your real data into the latent space Z to find the anomalies. Let's see how to do that. Here, like in the paper, we describe this one, but let me explain it in a like plain language without going to that complicated thing, right? So first of all, what you have is your data is in the real space, right? But your generator takes data from the latent space or the random space to the real space, right? What you need is you need a function that can do the opposite, like x to the z. Like you want to map your real data into latent space. The problem is you do not have that kind of functionality in your generator. So generator, you need this function actually. More specifically, you need inverse function that will map your x to the z, but you don't have that kind of function. So now what do you do? One trick is you can use similar idea of like how we train the other deep learning models, or how we train the discriminator. What we do is you take a sample, real sample, but let's say this is our real sample, right? Then you take randomly take a point from this like random noise, and then ask the generator so during this time you freeze the generator and discriminator. That part is freeze now, right? The training is done, generator and discriminator, they are frozen. So that means the generator and discriminator will not learn anything from this part of the model. So you take a random sample from here, and the generator will generate a sample. Now and that is completely random sample. So that random sample is, say, that looks like something maybe this, right? So which is quite different. Now you say, okay, you made a sample, but that is quite different from the original one. So what do? You take the difference, you estimate the difference between them. I will show you how to estimate that part, but bear with me. So you estimate the difference between them, and based on that you use stochastic gradient descent to tell, okay, you sample from here, that's why it is very different. Let's sample from something maybe here, right? And then see what sample it generates, and then calculates the difference between that one. And then again you use stochastic gradient descent to move it little bit different. So if you do this many times, you will see after exploring this thing, then it will find this point here. Maybe just the point is lying here, right? So if you sample from here, and then the generator will generate a sample that is similar to your real data, right? And then that is the best match you can find out, or your generator can give you the best real like generated data which is similar to this one. So at this point, for this specific sample, you stop, and then you take the difference between this generated data and then the original data. The difference is called anomaly score. And if that anomaly score is high and that exceeds a threshold, that will be considered as anomaly. Otherwise, it will be a normal data point. So that's what we are explaining here, right? So to analyze your model, like to find out this sweet spot where it will give you the best close point for your real data. To find out that one, we need to find out what is the difference between them, right? So to do that, we use two loss function. So one is called residual loss. In the residual loss, you take the absolute difference between the generated data by the generator and the your real data point. So what is the difference between them? This is called residual loss. And then and then we use another part. So this part comes from the discriminator. So you take the second last layer from the discriminator, right? So let us call that function of x. That will give you the second last layer representation from the discriminator for your real data and also for your generated or fake data, right? So now this two representation, you find their absolute difference between them, and that one is called discrimination loss. So now you have two loss, residual loss and discriminator loss. You add them up or in a weighted sum fashion. So we take the weighted sum between them, and that is called your the loss for anomaly detection, right? Loss function for anomaly anomaly part. Now, if you do this many times, you will find a point. Let's call that. So this one we call z lambda, right? This point. So if you run it many times, after some point, you will move to a point where you have this z big lambda, right? Z big lambda. That is like final state where you have like most possible close data points generated from the generator. Now you at that point you take the residual loss and the discriminator loss in a weighted sum fashion and then use that as a anomaly score, A of x. That is your anomaly score. So if you do that, so for this signal, for example, you can see these blue lines, the blue curve. That one is your loss function or loss between your generated data and the real data. Right? And then this green line that shows you the ground truth. That means 0 means no anomaly, 1 means anomaly, right? So at this point and this point, there is anomalies. Now you can see these 2 points are very high peak. Now if you put a threshold here, right? This one is threshold, this orange line. If you put a threshold and then any line or any loss that goes beyond this threshold, we'll consider that one as anomaly, right? So you can see this point goes beyond, so that one is one anomaly, and there is this point goes beyond, that one is another anomaly, and this and this, and there are anomalies. So you identified 1, 2, 3, 4 anomalies, but in your original data there are 2 anomalies. So that means 2 of them are correct and 2 of them are false positive. Right? So and then you use your different evaluation metrics like to see what is the accuracy for this anomaly detection model, right? So if your anomaly detection is high enough, then you use the model, or otherwise you change here and there, and then maybe you get a better model. Right? That's how we do it. So to do the experiments, we collected data. Like in this paper, we use data from NAB data collection. So in the NAB data collection, you have data points like you have 58 data collection, and then on average in those data collection you have data points that are like data sets that have 1,000 to 22,000 data points. The smallest one is 1,000, and then the longest one is nearly 22,000. So you have different variety of data set. Right? And so there are this many data points, 365,000 data points. All this data collection, they come into two different kinds. So one is synthetic data, another is real data. So there are 46 collections that are real data. So in these experiments, we used only the real data because we want to see how it performs in the real world, not just the synthetic world, right? So we use the 46 real data collection. And another thing is all the data points are annotated. That means the data set tells you whether a given point is anomalous or not. But we want to use this 10 again in an unsupervised fashion. That means we don't want to use those annotation in the training process, right? So we train the model without any annotation. And after training is done, we test the model using those annotation to see how well it is performing. Okay? So that is our data collection and setting. And then to see how well it is performing against other models, we used 8 baseline models. You can see that one is MADGAN, so which is similar to Tanogan, but we saw that our Tanogan performed better than MADGAN. We used autoencoder. As I said, autoencoder is very usually this one is very successful in variety of data. So so we need to see if our model can give better result than autoencoder. And then we did some other things like vanilla LSTM. We used isolation forest. So vanilla LSTM is like a simple LSTM used for forecasting in a forecasting fashion to see how to identify the anomalies. And then you have isolation forest. It uses like tree-like branches to separate out the anomalous data points. And then Gaussian mixer model that uses Gaussian mixtures, like a number of normal distribution in a mixer fashion to identify the anomalies. You have one class support vector machine, a bidirectional LSTM in GAN. So it is bidirectional LSTM GAN. We have CNN GAN. So all these models. So here we show you the experimental results. You can see this one, the top one. This is our Tanogan, and you can see and all these plots here. What it shows is different for different measurements. For example, F1 score, AUC or area under curve, Cohen kappa, accuracy, precision, and recall. For all these measurements, how our model is performing against other models for cumulative data sets. So cumulative means what if you take zero like 10 data sets, and how your model Tanogan is performing against other models. If you take 20 data sets, 30 data sets, 40 and 48, like, so if you use 48 data sets, and how your model is performing against other models. So you can see this for this cumulative graph, Tanogan is always performing better than other models. Right? Sometimes it is significantly better, sometimes it is marginally better, right? But it is performing better than other models. So this is the cumulative result. And then here we show the pairwise performance. In the pairwise performance, again for F1 score, we are doing it for F1 score, but for what we are doing is we comparing our Tanogan against one of other model, like Tanogan against MedGAN, Tanogan against isolation forest, and so on, right? So you do that thing. And what it is representing is if each point is representing one data set, and if the point is inside the dark or the gray area, that means Tanogan is doing better for that data set. Like Tanogan is doing better for the corresponding, like better than the corresponding model. If the point is on the line, so that means both of the model are doing better, same. So, right? And then for all these models, all these 8 baseline models, you can see Tanogan is performing better for most of the data set, right? For some of the data sets, maybe other model is doing a little bit better. but most of the time Tanogen is doing better. And now, after that, we wanted to see if there is any influence of the size of the data set and also the type of the data set, those things, right? So here in this figure, what we did is each color represent a category of data set, right? If like blue means one category of data, pink means this purple means another category of data set, right? So the category, and then the position in the x-axis, it represents how many models were defeated by Tanogen, right? So Tanogen performing better than how many models that represent the x-axis, the position in x-axis, and the position in y-axis represent the size of the data set, right? Now, if you look into this figure, you can see if the data set is big enough, like after some certain point, like after the size is 5,000, data point size is more than 5,000, Tanogen is beating most of the baseline models, right? But if the data set size is small, 5,000, then for some cases, Tanogen is beating other models. But for some of the cases, some other models are doing well. And for if the data set is very small, because Tanogen is based on deep learning model, you can obviously it has tendency to overfit. So in that case, very simple models, maybe like isolation forest or maybe one class support vector machine. Those kind of models can give you better result. But if you see even for those small data sets, Tanogen is performing better than other complex models, right? Like the MADGAN and those kind of models. So overall, if you think Tanogen is performing better. Okay, quiz time. So this one says, what does a GAN data? What does a GAN detect? Sorry, how does a GAN detect anomalies? How does a GAN detect anomalies in time series data? Oh, okay, so one, yeah, I think Rich already provided the answer. So one question was about slide deck. This is part of the slide deck that we presented in the morning. So it's just in the same slide deck. Just this part is, I kept it for the hands-on part. Okay, so so one question is why binary cross entropy for this one. The reason is you can see our discriminator that has only two classes, whether a data point is real or not. So if you have only two classes, you will use binary cross entropy. If you have multiple classes, obviously you can use like cross entropy for multiple classes. You will, yeah. Is there any other question that are... Okay, so I will show you how the data looks like. Like I will do those things in the like coding part. We are now like trying to give the idea of how it will work, and then in the coding part, I will show you the data and code and everything. So then you will see how the data looks like. For okay. Okay. So in the GAN, how do we detect anomalies? We use the generator to learn the general distribution, and then the discrepancy between generated data and the original data is used to flag the anomalies. This part we already discussed. We use GAN for anomaly detection because it is flexible. It can model complex data distribution. It can give more accurate like model. In other words, the accuracy is better. For all those things, we use GAN for anomaly. So there is a question about GAN, nanoGAN, and those things. So I'm not sure what the question meant, but let me try to answer it. So the nanoGAN was published long back. Like we did the experiments in I think 2018, and it was published in 2020. So obviously there are many models now, more advanced models that are being used. But in this case study, our plan was to present a simple GAN model that works well, easy to explain and implement during this session. That's why we chose this one for this session. Okay, so let's now go for coding part. Let me try to do this. So for the hands-on part, okay, now let's start with the data, right? So let's see how the data looks like. Okay, can you see my Excel sheet? Okay, thank you. So here you can see you have timestamp. You have two columns here, right? Timestamp, that means the date and time, exact time, and the value of a sensor, right? This is a value coming from somewhere, right? So and then you have many those time sample and corresponding value, right? So you can have many of them. So this whole thing is one time series, or you can consider it as one data set, right? So for this one, you can see how many points we have. We have like 7,269 data points. Okay, no, 60, I think 67 data points. Yeah, so you cannot put this whole thing together into the system, right? So we will do two things. One is obviously timestamp. We just need to know that which one is appearing first and second, which one is second, third, and so on. So in that case, we can remove this. This one only helps us to see which one is at what position, right? The sequence, to determine the sequence. Otherwise, this column you can delete. Another thing is for the value part, we will split it into windows, right? Different windows to train the model. So that is how our data looks like. Let me minimize this one. And then I will use this Jupyter notebook. It should be somewhere. Yeah, here. So what I will do is, because GAN is a little bit, two things. One is, if you have the code, and this specific code that was shared with you, that one is customized for running on CPU. But if you want to use the GPU version, that one is available on this link, code link. See, code link, or this is the QR code for this link. So if you go there, you can download the GPU version. If you have GPU, you can run on GPU and it will run much faster. But Yeah, I thought that maybe not everyone is having GPU. So in that case, I made this CPU version, right? So then you can use this one. Okay. So for this one, what I will, okay, let me share the link on the chat box. So I need to do it. Okay, now what I do is I go one cell at a time and then run it, and then explain the another cell and run it. I do in that way, but because in because it is GAN model, some of the cells will take a long time. So for that reason, what I will do is I will go and explain each of the cell. After explanation is done, I will let you run the model, and I will run as well during that time. And then during that time, if you face any problem or anything, we can discuss. I can try to help you to resolve the problem and so on. Okay, so okay, here, so you can see in the beginning, you just need to load all these um, libraries, right? That will help us to do the modeling or write the code. And then as I said, there will be two architecture or two module for one is for generator and another is for discriminator. So generator and discriminator are two significant part of this practice, right? So what I will do is I will practice explain the generator and discriminator first, and then we'll go to how to train it. So let's see the generator and discriminator code. So I have given you all the codes are shared already, and the link is already shared. You can see it there. So the first one, the LSTM generator. So the generator is available on recurrent underscore modules underscore pyramid in that file. So I think all of you already know how to do. So it is written on PyTorch. It is very simple to write and follow. So you define the class LSTM generator, and then it is type of module, you already know. And then you you define the init function where you do the initialization. So in the initialization, you tell them what is the in dimension. In dimension means how many features in your time series data. For the NAB data set, actually you have only one feature. That means only one value for the timestamp. But for other data sets, you can have several dimension or several features, right? So that is like in dimension. And out dimension means when your generator generates data, how many features it should generate. So usually in dimension and out dimension should be similar, so that you generate the realistic or similar data. And then you define, as I said, you define 3 layers of LSTM. LSTM layer 1, so LSTM 0, 1, and 2, so total 3. And then you define what is the hidden state size, right? Hidden size. So as I said, 32, 64, 128. So that like you start with the smaller and go a little bit bigger and bigger. That's the way we defined it. And after that, you use a linear model that will give you the output. So that will take the last layer from the LSTM and generate the data, right? And then the output data, obviously you can see output feature will be output dimension. So how many features it will generate. And then you write your forward function. So forward function is the function that will run during the training. So what you do is you need to define the batch size. So and then sequence length. So sequence length, say, as I said, we will run a sliding window. So if the sliding window is say 60, size is 60, then the sequence size will be 60, right? That many time step that we will take at a time. So that is sequence length. And the batch size is like if you have a big GPU, then you can use a bigger batch size. Otherwise, you can use a smaller batch size, like how many samples you will process at a time. And then you initialize your torch, right? For hidden states. So the LSTM has two hidden state, H0 and C0. I'm not going to that detail, but just letting you know that you need to initialize that one with zeros. So you can see for this version, I removed the device, like that means GPU. I commented that one, so that now it will run on CPU, right? So if you use 2 and then provide the device, let's say GPU, it will run on GPU. Okay, so initialize this hidden state, and then you can see you call this LSTM with these two hidden state, and then your input data, right? So your input data is coming from here. So you do that, and then you get the representation from the recurrent. So it is you can see the hidden state. It will return your hidden states and the output. So output from the LSTM, and this output goes to the second LSTM, and the output from second LSTM goes to the third LSTM, right? So and then you have the recurrent features. That is like output from the LSTM. And then that one goes to the linear layer, and to send it to the linear layer, you need to flatten out. Like here I'm doing the flattening, but there are default functionality for flattening. You can just call that flatten function. Right, when I was writing, I think that time I think the flatten was not available, maybe that's why I just manually flattened. So you can use that function, or you can manually flatten it. And after that, after flattening, you send it to the linear function, linear layer. You take the output, and then because I manually flattened, and then I manually stack them again. So I split them into batches again, and then return the output here. So when I'm returning output, I return the output. That means so that was like features, like output feature. Also, I'm returning the latent space as well, the second final layer from the latent space. For some cases, we will use this one. We'll use this one actually during when we estimate the anomaly score. That time we will need this part. For the training part, we will only use the output part, right? That's why I'm returning both of the thing here. I need to define them now. Similar for the discriminator, you initialize the things, but now we have only one LSTM layer instead of 3, right? And then obviously you have batch size, sequence size, initialize your hidden state, and then you send it to the LSTM layer, and then flatten to the linear layer, and then the stack again, and then return the output and the second last hidden layer, right? So that's what we are doing inside the LSTM or the GAN part, right? Like generator and discriminator. Now, one question was, how can we do it for text and image and so on, right? So you can see here LSTM is defined for to take like one channel, but if you have multiple channel, you can you just need to change here. You need to change your LSTM accordingly. So usually for image we do not use actually LSTM, we usually use CNN, right? So instead of LSTM you can use CNN, and then you just change the CNN layer. So maybe you use a couple of CNN layers and then send it to linear layer, and then generate the output. Same for the discriminator. So that will fix it. If you are using text, then obviously you can use the LSTM for text as well. So in that case, you have if it is text, and each word will be represented by some embedding, right? So in the embedding, if you have 10-dimensional embedding, then your in dimension will be 10. If 100 dimension, it will be 100, and so on. Oh, I need to end that. Okay.
Yeah, if you just zoom, make it bigger.
Okay, sorry. Okay, I hope you can see the text now.
Yes, we can see.
Okay, thank you. Yeah, my monitor is bigger, so I didn't realize that the font was showing small. Okay, so this part is done. So we defined all the discriminator and generator, and now let's go to. So we'll go to the more the Jupyter notebook. Before going there, I will explain another part. So for the data, so this is the main part where you will need to customize. So if it is say NAV data set, it has a specific structure, right? So you need to define it. If it is other data set, then you will need to change here, right? So you need to define your custom data set that will read and represent the data set, and then your model will take the data accordingly. So let's see here. So when you define the like data set in the PyTorch, you must have these two functions. One is the length function, len, that will return the length of the data, right? And then you have this this function get item. So given an index, right? Given an index, it should return the x value. That means um, the input data, and then y value, the your target variable. So in for this time series, because we are going to use it in unsupervised, we will simply you can simply ignore this part, or you still need to return it, but you can return any data. It doesn't matter, because we will not use this one in our modeling, right? This one will be just there. If you do not have like annotation, you can simply send maybe -1 or something, because we will not calculate this part. We will only calculate this part. But because of the requirement of the dataset function, this library, you need to have this function, right? So this is the two like requirement. And then other things you do yourself. So in the initialization, what you do is you read the data. So based on your data set, how you read it. So I have CSV. So I defined a function that can read my data. I read my data here, open the file, and then read the CSV. And also for the target variable, I have in JSON. So I read it from the JSON, right? So target is read here, and the right. So I read the x and y. X means input, and y is your target variable. So I read it here. And then I do another thing. This is called unroll, which is actually splitting my data. I'm splitting my data into chunks of, like, because it is a long sequence, so I split into smaller sequences, as I explained earlier. So this is unroll function that will do the splitting. And then assign anomalies. So this part is because we will be doing so our original data, like how the data is provided in the NAB, that is window-based anomalies. So it says the point where the anomaly starts and the point where anomaly ends. So I converted, I took that interval and convert it into points. Like all the points inside that interval will be anomalous. So, this is what I'm doing here. It is not complicated. Another thing, as I said, to make it stable, I do the normalization of the data. So the variable will be within the range, within a specific range. So it is minimax normalization. That means the data will be within the range of 0 and 1. Just normalization, nothing fancy. Okay, so done. So what you do is you read the data, and then you get your x and y. For the x part, see, I use the window length of 60, and then I did the unrolling. Okay. So here I'm doing the unrolling. Define x and y, and for the x and y, you do the unrolling. After unrolling is done, we take that as x and y. So x will be a sequence, y will be a scalar, like 1 point. Y will be 1 point for each sample. Okay, so let's go for the Jupyter notebook now. So what do? We import all the libraries needed. You can see I'm importing LSTM generator, LSTM discriminator from my file models start recurrent underscore models underscore py pyramid, and the NAP dataset. Those are custom, right? And others are actually default ones from PyTorch, nothing special. Okay, now for the we define some settings. You can define them like any numbers as well. Just I defined as a class, doesn't matter. So number of workers, that means how many processors I am going to use for running my model. Batch size, what is the batch size? Epoch, how many epochs I want to run the model. Learning rate, remember we said we can use different learning rates, and that means we start from that learning rate, and then we will be using Adam optimizer that will adjust this learning rate during the training. So usually if you usually we try to start from a very small learning rate, and then if yeah, if that works, fine. Otherwise, yeah, we can make it smaller, or if we see that we don't, if the model is very slow to train, taking a lot of time, then maybe we can increase the learning rate and so on. We can use those things. And the CUDA false, that means we are going to run on CPU. Manual seed, I defined the manual seed, but I didn't fully utilize the manual seed. Yeah, you can see that we need to initialize some of the weights. So if you and for my case, I randomly initialize them. But if you can use a specific seed so that every time you run, the initialization will be the same. You can do that as well. But yeah, for my case, I didn't fix the random seed for the initialization. I defined it, I used it for the torch part, but not the initialization part. Okay. And then here I'm defining the files. So NAP dataset has all the files. I'm here I defined one category of files. This category of files defined, and then I will use the file to train the model. So here I'm defining the location of my file, the file name and the location, those things. And then data settings again, so define the base and the file name, and then key means actually the category of the file, and then we will use the key to get the a target variable. That one is in a JSON file. So for those things, so these are all related to your data set, like how you read your data set, where the data set is sitting, and so on. Okay, now after that you define this NAP dataset. So there you send these settings, and the NAP dataset class, inside that class we have all the functionality that will read the data and assign it to this dataset variable. And then you know that we need to we need to use the batches to stochastic gradient descent. So to make the batches, we use the data loader from the Torch. So you use the data loader that will give us the batches. So that's it for the data part. And then, yeah, for this one, we are going to use CPU. You can use CPU if you need. Sequence length. Sequence length is our window length. So we define the sequence window length of where did we define it? Yeah, here window length is 60, right? So you define this window length 60. Okay, so that one is sequence length. In dimension is number of features. So that those ones. Now, after that, what we do is we create these two variables, net D and net Z. They are actually discriminator and the generator models. So you define the model. You need to give this like device name and then the input variable. And then for the generator part, what is the input dimension, what is the output dimension, and then device. So you do that and you define these two modules. And then you can see their structure here. You can print out the structure. So you can see for the generator part, you have 3 LSTM and the linear layer. And for the discriminator part, you have 1 LSTM and linear layer. So that's it. And then you can see in the final layer, we are using sigmoid, right, for the discriminator. And for the generator, we are using 10H. So this is the part, remember in the Wasserstein loss function. If you are using Wasserstein loss function, you don't need to use this sigmoid. You use sigmoid if you are using cross entropy loss. So this is where you will change to use the Wasser stain loss. And then you can see BCE. So we are going to use binary cross entropy loss for this one, right? So we define that and call it as criterion. And then for optimization, we are going to use Adam optimizer for both our generator and discriminator. So optimizer for D and G, we define these two. And then there you need to define the learning rate as well, right? So you define those things. Now, let's see how we train it. Now, for the label generation, for the generated ones, we will label them as fake labels. So the fake label will be 0, and for the real data, we'll label them as real label, which is 1. So 0 and 1, right? So we'll do for each sample, as for each data point, if it is generated, we'll call it 0. Otherwise, we'll call it 1. If it is real data, we'll call it 1, right? Okay, now we run through the number of epochs. If you have 30, I think I defined 32 as epoch, so it will run for 32 iteration. And then for each iteration, you run through all the data, right? So you take the data loader. So in the data loader will give you two things. One is the index, because you enumerate actually in index. Data loader actually gives you X and Y, the input data and the target data. But because we enumerate, that's why we get the index as well. Okay, now inside this loop, you define your discriminator as 0 gradient. That means initially you define the gradient as 0. That means you're not moving anywhere. You're just initialized gradient 0, right? And then your X is so you take the X and let us call it real, but you can keep it X as well. During the coding, you understand that this one, when I did, this one was for research purpose, the coding. So we do here, there, change here and there, many things. So that's why code is sometimes, little bit messy, not that very clear. But overall, it is not that very messy. We can follow it actually. So and then the real, you get the size, so which is actually like batch size, and then the size 1, which is like sequence length, obviously. And then what we do is for the batch size, so for each sample and for each data point, because it is the real data for this one, the X. So we define a vector, torse vector or torse tensor, whatever it is, torse, you can call it tensor as well. So you define a torse tensor that defines all this label as real level or level 1, right? Real level is actually value 1. So that is the label now. Now you ask the discriminator with this real data and ask it to predict whether this is real or not, right? So that is your output. And then the criterion will take your predicted output, that means whether it is real or not, and your real label. The label is like you define that because it is real, you define this one as 1, right? So it will take this one and the predicted, and it will calculate the cross entropy, binary cross entropy loss between the predicted one and the real one. So that one we call error of the real data. And then you know that if you call error real dot backward, that will do the back propagation. That means it will calculate the gradient when it does the back propagation. And after, when you call the dot step, this function optimizer dot step, that will update the weights inside your model based on the gradient. So yeah. And yeah, that's done. For dx, this part we take the mean of the output. So this one is actually visualization purpose only. This part is not important, so we'll print out this thing in the end to see how the model is working, right? That's why doing this part is not important, not that important. Okay, so we are done with this one. And then for the generator, we need to generate a noise, right? Z, remember, that's the noise part. For that one, what we do is we actually use a Gaussian noise or normal distribution of noise, And from the Gaussian noise, we sample, you provide a mean of 0 and a standard deviation of 0.1. So it is a like very narrow Gaussian. You need to take a very narrow Gaussian, and from there you sample your noise, right? And then you send your noise to the generator netz and call this forward function, right? So that means it will take the noise and generate the sample or the fake data. The fake data is generated, and then you send this fake data to your discriminator. Now for the fake data, you label, you generate label as fake label, like 0, right? So this is your fake label. Now you call this criterion. That means you estimate or calculate, actually calculate the binary cross entropy between your the predicted one. So whether your discriminator could predict it a real or fake. So what is the probability that this one is real, right? And then your label. And then based on that one, the difference is the error, and we call it error of fake data. So you have this one, and then you call this back propagation. You can see error of fake, right? This one is related with this output, and this output is coming from this one, right? netz, right? So that means based on this one, you update your discriminator again. So that's why you can see the discriminator loss has two functions. One is for real data, and another is for fake data. How well it could identify the fake one. So you did this part, right? So you update it here, you update like back propagate, and then you do the step, and then you update. Couple of lines here. This is again for visualization purpose. They are not important. This visualization purpose, I'm taking the mean of this generator output and then the total loss and those things. This is just visualization. Okay, now now go to now let us update the generator. So in the generator, you say gradient equals 0, and then you take the noise, you take a random noise from the Gaussian, and then you send this noise to the generator, and the generator will generate the fake sample, right? And then you label that one as fake. Sorry, you label that one as real, right? So you pretend like that it is a real data. Now let's see whether your discriminator agree or not. If your discriminator agree, that means it could not identify that this one is actually fake data. It said it is real. So in that case, this is good for a generator. But if the discriminator disagree, that means it could identify that it is a fake. In that case, we will penalize the generator, right? So you calculate the criteria between your predicted output from the discriminator and the label, right? The label fake pretended as it is a real, right? And then you calculate the loss. And based on this one, you can see this error and this output, right? So this is the criterion. Now you calculate this error, right? After that, you optimize this part. So which one you optimize? See, now you're optimizing the generator part. Previously, see, this is the difference. You optimize the discriminator part. See, here and here, you optimize the discriminator part. That means for the loss, any loss it makes in this two step, the discriminator is penalized. Here, you are penalizing the generator. You can estimate the loss from the discriminator to see if it can find out or not, and based on that one you penalize the generator. So that is the difference. And then you print out what is happening. So if you run this one, it will train your generator and discriminator. After training is done, we'll need to identify the anomalies. So when the training is done, that means now your model know the general distribution of your data set. So here again, we define some of the parameters, like how many workers, what is the batch size. Now, for the workers, still you can use multiple machine, doesn't matter. For the batch size, if you use one batch, then you can take one batch and calculate corresponding loss. That's fine. But if you use batch size different than one, then you will need to adjust your code so that it can calculate for multiple instances, right? So this part, remember that usually in my code, the batch size for anomaly anomaly detection part, that should be 1. If you have more than 1, then you will need to change the code so that it can handle that part. Okay, again, like you have the generator and discriminator. For some reason, I don't know, I changed the name, generator. I call now generator netz as generator, netd as discriminator. I don't know why I did it that time, but yeah, same thing. Netz or generator is same thing. Discriminator and netz, netd are same thing, right? They are same variables referred in two different names. Okay, so this is where my testing data set is lying. All the testing data set. This is where the label is sitting. This is where the data is sitting, and so on. So you can read the data. So you read through the again data set, NAP data set. You read this, and then you do the batching if needed. Batching. Okay, so after this one is done, we calculate the anomaly score. We define a function that can calculate the anomaly score. So how do you do that? Remember, in the anomaly score, we have two things. One is residual loss, the loss between the generated data and the real data. So difference, we take the we take the absolute difference between the real data X and the generated data, the difference between them, absolute difference, and then because we are taking in batches, that's why we take the sum. Right, that's right. So this is done. This is residual loss, and then there is discriminator loss. So for the discriminator, you can see now we are using those feature. Remember, LSTM we had that second last layer feature representation. So we take that feature representation of the discriminator. We send the real data and take the second last layer representation. Same for the generated data. What is the second last layer feature representation? So now we take the difference between them. So feature representation for the real data and the fake data, and then what is the difference? And this one is called discrimination loss, right? So you have residual loss and discriminator loss, and then we combine them with a weighted sum. So that weight is called lambda, right? You can adjust this lambda value based on your data set and application. So that is our total loss. So based on this one, we'll calculate the anomaly score. Now for the anomaly part, remember we need to inverse map the data to the latent space. So what do you do is you randomly take again from a normal distribution. You take a random sample, right, Z, and then you send it this random sample to okay. So because now another thing is we will only update this Z, right, based on our loss. We will not update the generator or the discriminator. We will try to get a Z that can give us the better sample, which is similar to our real sample, right? That's why we need to send it to this operation, like optimization function, right? So which is like Adam optimizer. So that will find out the closer point. Okay, now what we do is you can change this value. For my case, I run this for 50 times. So we take this random sample, right? And then we ask the generator to generate a sample, which is fake sample. And then we find the anomaly score between this fake sample and the real sample, right? Real data. And then based on that one, we update the Z value. The Z will get updated. And if you do it 50 times, so you can define some other thing, right? So if you run it for 50 times, then you will go to a point where the generator will give you samples that are very similar to the real sample, right? So that one at that point, like after this loss, after this like loop, we finish the loop and then we calculate the loss. So this loss is our the anomaly score that we will use as anomaly score. That's why loss list we added this anomaly. So that's what we are doing here. After this, so we have all the anomaly score for the whole data points, all the data points. Right? We're done. This one is long. Okay, so after this point, let's do some visualization, right? So we use the matplotlib to visualize our, see, we are visualizing loss. What is the loss? Like loss score, like here is the blue point, blue line is the loss score. We define the y. So y is actually like the y value, like this green line, what is the like ground truth, right? And then we define a threshold. So threshold value I got like 10.2. Based on your data set, you can define another threshold. So the threshold is like this orange line. Now you can see for this one, this part of the like anomaly score that goes beyond this threshold. So you can identify this part as anomaly, and you can say this actually corresponds with your ground truth. If you visualize that part, you can see this part, all the points in this part is identified as anomalies, and this corresponds with our ground truth, right? So this is like original signal. This is the original signal. So interesting thing is, you may think, okay, I have the original signal, and then if the signal goes beyond a threshold, then I can identify this one as anomaly. But that is not true. You can see these anomalies are actually smaller than the higher value, right? Higher value in this range is smaller than, but still they are anomalies. The reason is their pattern, right? So the pattern is something like this, but here the pattern is quite different than all the other patterns. That's why this part is identified as anomalies. And also human leveling, they identified this one as anomaly, right? See, that's the interesting part about this kind of models. They can learn all these patterns. Even you have multivariate time series, very complex, and still it can find out the pattern, and it can identify which is deviating from the pattern, right? That is the beauty of this kind of model. So that's what we have done. This one is actually we are calculating the accuracy. So we calculate what is the true positive, false positive, then accuracy, precision, recall, F1 score, all these things, right? So you can see for this specific signal, you have accuracy of 78%, not that bad, right? 78%, and F1 score 71. Looks good actually, but yeah, you can adjust here and there, change model structure and so many things to make it a little bit better. That is possible. Yeah. So that's the part where yeah, it goes. So let me check the time. So we have spent 2 hours, I think. Yeah, 3:30, 4:30, 5:30. Okay, more than 2 hours. So now let's run it, right? You have the code. You can run it on your side, and then if you are facing any problem, you need help or anything, you can let me know. Let me run it on my side to see if it is running smoothly. Let me restart kernel and run all cells.
You may give them 5 minutes break so that they will be ready with the code and everything.
Sorry?
You may give them a 5-minute break.
Oh, okay, that's a good idea. Yeah.
Yeah.
Yeah, I think that is a good idea. So let's have a 5 minutes, okay, or 10 minutes?
I think 5 minutes, okay.
Okay,
And
let's
you
have
can
5 minutes break. That's good for me as well. Yeah, let's have 5 minutes break and then come back and yeah, run the model and then see what happens. Yeah, thank you.
Okay.
I will stop sharing here. Okay, let's back to the work. This one. Okay, so let's do this. Restore and clear output. So I'm going to clear out all the things. Now let's run it. So you can run this one, loading all the libraries. Yeah, so successfully loaded all the libraries. Define the setting, and then this one. File list. That's it. Okay, now this part, when I call this one will read the data. So we want to see the shape of the data for input and output. It is reading the data, so reading is done. You can see it has 17,990 data points, and the sequence length is 90, right? So each data point is 60 length, and then it has only one feature that or one column, right? And then this stores the target value. It is just one. This is a vector actually. Or like scalar value list, you can say. So this is the shape is you can see the number of points here and number of points there is the same. So this is like target variable. Okay, now after that you define this like window length and this thing. Okay, create the model, the two module like generator and discriminator. So done, and then you can print out their size, architecture. So you can say LSTM one layer, and then and then the linear layer. So LSTM in the discriminator you have LSTM layer, and then linear layer or fully connected layer, whatever you call it. And then after that we use a sigmoid function, right? If you remember, then the sigmoid. Yeah, 5 minutes back was there. So in this one, yeah. So see, your output goes through this sequential, the linear layer, right? So see, you have this sigmoid here, right? This is the sigmoid that I'm talking about. This is the sigmoid. Sigmoid, and then here you have LSTM, 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 3 LSTM, and then one linear layer. And after that you have 10H. So 10H will normalize your data between -1 to 1. And then the cross entropy. This one, I think, yeah, code, yeah. I think now better. You can see the code now. Okay, so and then this is your binary cross entropy. Your optimizers. So remember, you need two separate optimizer, one for discriminator and that is for generator. If you use the same optimizer for both the model, then your model will behave very funny. Okay, now after that, we do the training here. Let's do the training. So it is running. It started running. See, my code is old, like now some of the functionality already deprecated. If you're facing any problem, please let me know. So this one is running. By the time it is running, if you need any help, I can try to help you. It will take quite a bit of time. GAN is slower, and another thing is it is running on CPU. If you are running on GPU, I think it will be much faster. The training time is more two reasons. One is you're right. We have two models now. That is one thing. Another thing is it is running on CPU. Obviously, running on CPU will take much more time. Another thing is because it is generative model, it needs more epochs. See, 32 epochs. 32. Usually, if you are training a classifier model, maybe 5 or 10 epochs is enough. But for generative model, it takes much more time to converse and try learn the distribution. So that is another thing. Sorry, epoch is 20. I got it wrong. The number of epochs is 20. So 20 is, yeah, usually within 10 we are done if we are training for say text classification. But for the GAN type of model, yeah, it is taking more time. And you can see you are running, actually technically you are running 3 models, right? So you run the fake sample, so the GAN like generator runs 1, and then run the discriminator, so 2 models, and then you run the discriminator for real sample, so 1 2 3, right? And then you run the generate again, so 4, and then generate for the run the discriminator for fake sample 5. So you are actually in each epoch you are running 5 models compared with like what we do in like general setting. So in that's why yeah, any GAN model is slow in training because of it takes this much complexity. You can say it is training. So you have discriminator loss and generator loss. So it is for fake sample. To run on GPU, you can get my GPU version of the code, the GitHub version. I have given the link on the chat box. I have the link here as well. I think somewhere. Is it? No, not there. Actually, here. I think I have the link is here. Yeah, so this is the GAN model. So here you have the model, the location where the data could be found, the Python, like Python, like Jupyter notebook, the data set, everything is there. You can download this one just from the code part. You can say download zip that will give you everything in a zip file. So here, yeah, so also it has a link to the publication both the published one and the archive one, and also there is a small video presentation. You can watch that one as well. That one is dedicated only for this paper. It was actually a conference presentation. It was published in a conference, so that is the conference presentation. You can get that, and that is the citation as well. So if you run this version, the GitHub version, that is like written for GPU version. What I did is I actually removed the GPU for running it on this machine. Yeah, so we have run 3 epochs, many many more epochs to go. Yeah, it takes quite a bit of time. That's why I explained everything before I run it. Otherwise, yeah. But the good thing is you're having your like enough time to run and ask me questions. You can ask me any type of questions actually. Like I have been working in this area for many years, more than 11 years I think. So yeah, I'm happy to answer any questions. And if I don't know, I can refer you somewhere where you can find the answer. GAN requires more data as well to train. Because in a way you are right. Like it takes more data, yeah, but the good thing is for the GAN, you don't need to label the data, right? So you have a bunch of data, and then you know they are real, right? You collected it from somewhere, that's why they are real, and that's it. So your discriminator will differentiate between real and fake. You don't need to label the data. That's why data is not a problem. Unlabeled data is abundant, many unlabeled data. Labeled data is scarce. You don't have enough labeled data. That is the problem. But unlabeled data is not an issue, I think. Only issue is computation. You need to run it longer time if you have more data. That is the thing. Cross validation. What is cross validation? Cross validation is okay. It is related to the like deep learning models, like supervised learning, right? Where you have a data set, and then the data set, if you train the model, after training, you need to see how well the model is performing, right? Simplicity good data, but easier to acquire because setting. Yeah, you're right. Yeah, because it is unsupervised, acquiring data is easy. Yeah. Okay, so to go to the cross validation, so you have like data, label data, and you're training a model. After training, you want to see how well the model is performing. So how do you know it? You need a test set, right? So how to get that test set? You actually, what you do is, given the whole data set, you split out a portion of data from your whole data collection, right? So you keep it aside, and then say 20% of data or 30% of data you keep it aside, and then you take the remaining data to train your model, right? And during the training, you can you need to fine-tune hyperparameters, and for example, how many layers, how many per second do we use, what should be the learning rate, what would be these, that, and many other hyperparameters, right? So if you tune the hyperparameters, how do you know that your model is doing well? You need to do the testing. Now one option could be you could use the test data, but the problem is if you use test data, actually your hyperparameter will overfit the test data. In other words, you are cheating with the model. Your model sees the test data before you deploy it, so your test performance would not be reliable. So what do you do? So from the training data, you again take a portion for validation, and then the remaining you use for the training. Now again, if you use say 20% again, see your data is reducing. You don't have enough label data. You keep aside 30% for training, sorry, testing, and now another 20% for validation. You have only 50% remaining to train the model. That is not very good thing, right? So you need a mechanism so that you can use the whole data set. You want to use this whole 70% of data. How do you do that? That is one question. And the question is, if you have only one set of validation data, maybe accidentally your model gave good performance for that specific split or for that specific validation set. If you change the validation set, maybe your accuracy will change. Now how to solve that problem? So one good solution would be instead of splitting for validation one portion, you do what you do is you do the cross validation. So in the cross validation, you split your data into n-fold. N-fold means, say if you want to use 10-fold cross validation, you split it into 10 portions, and then you take one portion as validation data, remaining portions for training the model, and then you do that. You take the second portion as validation and remaining data for training the model. You do it for all the 10 portions, and the error or the accuracy you get for all these 10 portions, you take the average and see how your model is performing for all these 10 portions, and that will give you a more reliable validation for your data, right? Hyperparameter you train, the model you get, that is more reliable, and you also utilize the whole data, all the training data set for both validation and training, right? And after that, after all these things are done, then you do test your model with the testing portion and then report what accuracy you get. And those kind of models are usually reliable, right? You have like thorough experimentation with the data. Can you please explain the latent space Z? Okay. The need of confusion metrics. Okay. So are you asking why do we need confusion metrics? How well it is resulting in case GAN other than previous techniques like CNN? These two questions, I didn't get the context. Are you asking that how this GAN is performing against other baseline models, like if I use LSTM or other models? If you are asking that questions, we show you the results and other things in the presentation, and also it is available in the paper if you're asking that question. So say we have the performance, sorry, against somewhere. Let me find out. Against all the other models, right? So we experimented it against other models, how it performs with like CNN based models, GAN, other GANs, and LSTM, and so on. Some of the traditional models as well, right? So that is the part. Another question is explain the latent space. Okay, now someone getting problem. True positive. Okay, so that one, yeah, I get why you're getting this, like true positive 0. That's normal. That's normal. Yeah, don't worry. I will explain why. So I think you are running the GitHub version of the code, right? So if you are running GitHub version of the code, you need to change a little bit. See, the one I showed here, that used this track equal 1. That means I am using this data set, right? This one. I'm using this one. CPU utilization, as you said, this one we experimented. I think for the first one, this setting failed to find out the anomaly, right? Yeah, and the GitHub version is actually hyperparameters are not optimally tuned. So you may need to like tune the hyperparameters to get the correct output. But still, if you for this one, I am using the same hyperparameter as the GitHub version, but I'm using the second data set, right? So if you use the second data set, you will get the positive anomalies as well. Right now, everything is negative. And the one, yeah, because you have false positive 0, that's why you are getting divide by 0, right? That is so the two solution. One is like if you get the positive, like true positive, then fine. Otherwise, you can add a very small number, epsilon, right? Very small number when you are dividing, so that it doesn't get divided by 0. Then it will fix it. want to know confusion matrix. So confusion matrix for this one, this is a okay, like I'm running it again. That's yeah. See, I showed the confusion matrix here, or you are asking what is confusion matrix? Oh, okay. So if you are asking about what is confusion matrix, that is like find confusion matrix gives you what are true positive, true negative, those kind of things, right? All right. And yeah, I thought that was related to like classification part, but I can answer it. So what happens is, what is true positive? So for example, if your model says a data point is true and your ground truth says it is true, then it is called true positive. But if your ground truth says true and okay, other way. So if your model says it true, and then if your ground truth says it is false, then it is called false positive. That means it is false, your model is saying it is true, right? That's why it is false positive. On the other hand, if you have if your model is saying it is false but it is false, then it is true negative. If your model is saying it is false but it is actually positive or true, then it is called false negative. That's how the confusion matrix is. So if you know the true positive, false positive, those things, and then using those things, you can calculate precision, accuracy, or recall and F1 score. So F1 score is simply the harmonic mean between precision and recall. You can see precision and recall, and then you divide. So you multiply them and then divide by their summation. So which is like harmonic mean between precision and recall. That gives you the F1 score. And if you are asking for what is precision recall, precision is how many positives your model could identify, right? So you say your model said 10 points as positive, but only 7 of them are positive, then the precision is only 70%. And the recall tells you out of all the positive, how many your model could identify. Say there were 20 data points that were positive and your model could only identify 7 of them. In that case, it will be 7 divided by 20 will be your recall, something like that. So this is like precision recall. So another question was about latent space. Latent space Z is actually, say you want to generate your data, right? And then you need to start from somewhere. Now you can start from anywhere. So you start from a random point and then try to calculate, like generate the data. Now what that random number could be minus infinity to plus infinity, right? Any number, but that will be a problem. It will take forever, infinite time to train the model. So rather what we do is we take a Gaussian. So Gaussian is, and then we take a mean and variance. So it will assume that your data is normally distributed. In other words, the data can be generated from a normal distribution, right? So in other words, the Z is your index for generation. You take a point from that Gaussian distribution, and your Z will, or your generator will give you the corresponding value or corresponding generated sample for that specific value, right? So and if you want to explore many complex situation, that will be difficult. That's why we use normal distribution, which is very simple one. Like Gaussian is very simple distribution. So yeah, that is what happening in the latent space. Latent Z space. Latent space actually means every latent space, but I'm talking about latent Z space. That means the random number that we use to generate our output. Okay, latent space is a For recall and precision, there is a problem, right? So for example, if you have data and then if your model says everything, say you have 100 data points, right? And then out of that, only 10 of them are positive. And if your model says all of them positive, you can see your model could identify all of them, right? All the positives. So recall is 100%, but you can see 90% of them are false positive, right? That is a problem. And now again, if you want to take precision, so precision, if the precision says precision is like how many of them are correctly identified, right? So you can say if it says all of them negative, you can say that it is 90% correct for precision. So there is a problem, right? If you increase the precision, recall will go down. You increase the recall, precision can go down. So you want a sweet point between precision and recall. So that's why we take the harmonic mean, which is F1 score. So that's why you will see most of the paper, they emphasize on F1 score because it can give you a balance between precision and recall. So harmonic mean will tend or bias towards the smaller value. If your precision is small, you will see F1 score is small. If your recall is small, then you will see F1 score is small. So that's why we use F1 score. And in terms of accuracy, is 70% good or not? That depends on your application. For example, if you are driving if you are developing a self-driving car, and 1% a mistake can lead you to death, right? So that 1% is very bad. On the other hand, if you are doing it for some simple task, say if you're searching in the Google, or you're searching for information and to see whether it is relevant or not relevant. In that case, if it is 70% accurate, it is pretty good accuracy, because out of 10, 7 of them are relevant. So you are happy with 7 relevant data points or 7 relevant documents. You don't want 100% accuracy, right? So 70% should be enough for that case. So you can see it depends on your application, where you are using. Oh, JSON, there is a JSON file. Yeah, okay, the good question, actually. So if you go to NAV dataset, right? And then there is these labels, right? And then it tells you where to find that level file. Yeah, it is, because I can't share the data. Data is not mine. It is from NAB, so I cannot share other data. So I just shared the link where the data is available. So you can go through this Kaggle, and then in the Kaggle, actually, yeah. Yeah, if you go through this label, the data is there. See, the data is there. See, this is the JSON, right? So you need to download it from there. It is because, copyright and other things, legal reason, I couldn't share it. But I shared it personally, like the data and the code is already shared. From there you can get it. So for example, if you go to the data, see this part, this whole folder is shared with you, right? So if you go inside, and then inside the NAB dataset, if you go to labels, and then if you can find out the JSON, there is the JSON. Okay, let's see what is happening in our code. So how many we have done? Let me see. Okay, not bad actually. We are done with 13 epochs. And then you will see another interesting thing. For the anomaly score calculation, that will take another bit of time, because again, you will need to run this generator and discriminator to get the score. And for each time, you need to run it for how many times? Here 50 times. So that will be quite slow as well. Yeah. So yeah, we'll be running, but yeah, good thing that we are discussing, explaining things. That's good thing. Okay, so I will come back in a minute. Thank you. Mm. Yeah, so if you are, as I said, if you are using this data, can you check if you are using this data set, like the second one? You need to use only this one. Like for this specific code, I tested only for this one, right? In other words, I checked the hyperparameter for only this one. For other ones, I didn't check for this tutorial. I checked only for this one. So if you are using this one, then I can like check what is going on. So as I said, the hyperparameters are like sensitive to dataset. You need to properly set the hyperparameter, and yeah. Yeah, I think because of the CPU version, it is taking much more time. See, if you are using GPU, you already finished it. I could actually use the GPU. I have GPU machines already. Let me try if I can run that one. That machine is not running right now. Yeah. I have a GPU machine. Looks like I cannot connect to that one. Neeraj Kumar, did you check which dataset you are using? Yeah, ambient system failure will give you 0. That I know, I tested, and I didn't have enough time to like fine tune the hyperparameters. But for this one, that CPU utilization, that one you can get some positive. Track one, so we have your CPU utilization. For the CPU version track equal 1, it should work. So the code that I showed before I restarted, you saw that there was positives and things, and I tested the code in this morning. So should work. Usually it should work, but in some cases, I don't know, because the random initialization, because of random initialization in one, maybe. But I believe it should work. If there is everything going correctly, it should work. Niraj. So if you're not getting, that would be funny. I think for tomorrow, I will try to use my GPU machine. Tomorrow we have another session, so for that hands-on, I will use GPU machine. That will be faster. CPU is really slow. Let's see how about other people. They're getting same. So mine is 18 epochs done. So while you are running, if you have any questions related to any machine learning questions, you can ask me anything. Not only GAN, you can ask me any questions that I can try to answer them. My machine has only 16 gigabyte of RAM. I didn't test like any other machine actually. So my the published paper I used actually GPU, and it was 12 gigabyte of GPU. For this hands-on, I tested it on my CPU machine with only 16 gigabyte of RAM without any GPU. How can we use GAN model multi-modal task generation? So the question is, what do you mean by multimodal task generation? Are you you need to tell me the modes that you want to use. For example, if you are generating video, so in the video you have image and then voice, right? So two modes, audio, text. Yes. But I didn't see any model that uses audio, text, video, everything. Usually, like as output, you don't expect text and video going together, because that is not very useful. People didn't try it. If you're talking about how to generate video, like the image and voice together so that it becomes a good animation or video, what it does, it takes different channels. So one channel will produce the video or the images, and another channel will produce the audio, right? So, and then for each picture or frame in the video, the corresponding voice will be generated in another channel. So two different channel, and then after generation, you combine them together and get the video. So for the text part, you may think, okay, why not just text subtitle, generate subtitle for the video? That is very simple. If you have voice and video, there are lots of models that can take your voice and convert into subtitles. So that's why usually that is not done. I didn't see any model that do three things together. But yeah, for input, you can take audio, video, text, everything that is possible. And yeah, it is just a number of channels. You just increase the number of channels. That should solve the problem. But if you are interested more, I can advertise myself. We have several papers for multimodal data. Let me show you. So if you go to my Google Scholar, right? And then let's see the recent publications. So this one, a novel multimodal fusion method based on uncertainty guided meta learning. So this one was published in Pattern Recognition, and this recently it was published. So you can read this paper how to handle multimodal data. Like one problem is, or challenge is, how to combine different modalities together. So we try to handle that problem here. And then this one is published in Neural Networks. This one is also a recent paper. That one is pre-gating and contextual attention gate. We propose two different mechanism of gating to fuse different modalities together. So you can read that paper as well. So these two papers will give you a good understanding what are the challenges in multimodality, how to combine them together, and so on. They're very good paper published in top journals. So it should be a good direction. But in layman terms, you use multiple channels, right? So if you are using it as input, what you do is you read text in one channel, image in another channel, right? And then maybe voice in another channel to stop it. Yeah, and then so you take it in three different channels, and then you fuse them somehow. One way would be you concatenate them together, you add them together, you use a weighted sum, and so many different ways to combine them together, and then send them to different layers of your neural network, and then finally get the output. If you are talking about generation, similar, you take the input. So that input could be a prompt, a noise, or something, and then your model will generate different things, and then you can dedicate different channels, one channel for video, or like an image, one for text, one for audio. So that's how you can generate. Is there any real-time generation system? Yes, there are many. So real-time means like computation is faster. So first of all, in GAN, we just talked about this in the lecture, right? That people are working with GANs to make it faster. So you can, first of all, we are using LSTM. LSTM is actually slow because it is the recurrent model. That's why it is very slow. So if you replace LSTM with something else, for example, maybe just feed forward neural network, or maybe attention, right? Attention head, and then you can get a faster model compared with LSTM, all right? So when I did work with this one, attention was not that like popular, or at least it was not being used in the time series. But now people using attention layer for time series as well. So that can reduce your time. And And also you can make your model smaller. You can have a pre-trained a layer that is already pre-trained, so you just fine tune over that layer, and so many techniques to improve the GAN. And beside GAN, there are much faster models. For example, you can use autoencoder. Autoencoder is much faster than GAN, but yeah, the autoencoder has a limitation that it assumes that the data is normally distributed. Your Latin space is normally distributed. The encoder decoder, so you encode it through Gaussian distribution and decode from that, or sample from the Gaussian distribution. So that is a limitation. But if the GAN is not limited for any distribution, GAN can learn any distribution, right? That is like much more flexible. So GAN is very powerful, much powerful. So yeah, so if you have a very small task and not much complicated, maybe autoencoder would be a good suggestion to use. But if you have a complex data set, obviously can help you there. Yes, so yeah, that part also. So the GitHub version, I think the data set is moved to the GPU as far I remember. So yeah, your data and model all needs to be in the same device. But I remember that I moved the data into GPU for the GitHub version, if I'm not wrong. Yeah, but obviously it should be in the same device. If I didn't move it to the GPU, then yeah, obviously you would need to move it. As I said, VA, a variational autoencoder, that that thing is the distribution you learn is assumed to be normal, right? Okay, let me show you the picture VAE, right? So if you're using VAE, try to find out the distribution space. Yeah. So see, if you can see this, so your encoder encodes your data into a normal distribution. So mu and sigma. Mu is your mean, sigma is your variance, right? So because it is mu and sigma, and then you use normal distribution to sample from here, right? So now if your data is not normally distributed, then your autoencoder or like variational autoencoder, that will be wrong modeling of your data. So accuracy will be low if your data is not normally distributed. But yeah, if your data is normally distributed, variational autoencoder would be the best solution, because it is much faster, and the prior assumption is same as your data distribution. Then yeah, go for autoencoder if your data is normally distributed. But if it is not, then yeah, that might be challenging to model with autoencoder or variational autoencoder. To use GAN in medical imaging, so what people do is, so for example, I didn't work with medical image. Let me confess first. No, but what I saw people using is, say, let me give a like random example. So say you have an X-ray, and then you want to see what if there is this variation. So there is a spot, and then if you want to see if there is a variation, what will happen, those kind of things, right? And the thing could be, say you took an image, and then that image is not showing relation to some other attributes. Then you can generate an image based on that one that can show that relationship, and so on. So in other words, GAN can because it can learn general distribution, so it can learn from thousands of X-rays, And then for a given X-ray image, then it can show you some variation that can help you for diagnosis or better medication and so on, right? So that kind of things people use GAN for. Okay, so this one, let me see if it is running. Okay, this part is done. All right, see that this part is done. So I have now trained for 20. Now we need to define this part. Generator, discriminator. Okay, so this is the testing data. And then for the testing data, we need to start this one. Right? And then this is the definition of anomaly score. And then we run the inverse mapping, right? So here we are doing inverse mapping to find the anomaly score. Any more questions? My model is still running. So we are doing the anomaly score part. It looks like training is done. So let's see the anomaly score. See, this in my case it is working. You can see. So my inverse mapping done. You can see everything is done, and then so I calculate those things. Invalid character. What is this thing? Okay. Now see, it is working. And then this one calculate the window base, and then let's see the thing. See, my true positives 14, false positive 0, true negative. There are these false negative. Some of them are missing. So accuracy is 96%. F1 skewer is 71. See, and not bad. It is working at my side. Data loader work exceeded unexpectedly. That means you somehow it overflowed your memory. So this error usually comes from the memory overflow. If you data is overflowing the memory, allocated memory, then it can happen. Data loader worker. Can you check your RAM size? What is your like memory size? Hmm, 16 gigabyte RAM should work. This is interesting. Data loader worker. Let me try to Google this one. Data loader is easily it should work. Oh, it says because of Windows variation. So if you use number of workers, like remove the number of workers, it should work. This is related to parallel processing. For some reason, your Windows cannot handle parallel CPU processing. So that's why you're getting this one. So they're suggesting if you use disable number of workers. So what you can do is you can set number of workers to 0. Remember, I set it to 4. If you set it to 0, then it should fix. So here, somewhere. Number of workers. See here, instead of 4, if you assign 0, then it will work for you. Yes, this is your location. Yes, where you put the data. This is my specific location. Yeah. So for example, maybe you put it in another drive or in the location. So you obviously you will need to update this one. So Niraj Kumar, did you change this part? I think this you need to change only this part, right? If you change this part, that should fix. So this is for my CPU machine. This is the location. For GPU machine, the D drive was the location. So you will need to fix this part. Okay, that's good. I hope after the change it works. Dataset.py, which one is dataset? Let me see. There is this nav dataset.py. Okay. So in the nav dataset, okay. Oh, okay. This part, yeah, you don't need to change this one. I didn't use it, I think. So this one I defined for some reason and then didn't use it, I think. See, it is not, yeah. So this one was for only for testing purpose. Yeah, that one's this part of the code is not important. That this whole part is actually not important. This one is only needed if you try to test it from the console. Any other issue that I can help? I think I have a paper somewhere that describes all these measurement techniques. Let me see. Like it's something in this paper. Yeah. So in this paper, I explained all these measurement techniques. See what is true positive, true negative, everything is explained here. So I will keep this link. Hidden layer tensor in CPU, okay. Oh, okay. Let me see. Module that okay. It is asking to make changes in module jetpack. Let me see. So we have the device.
That link for the PDF.
You need to make it. Okay, so um sorry, there was like technical issue. So yeah, for it looks like some people getting some problems. So what we can do is for those problems you can try home to like try to fix them. If you still cannot fix them, we can try to fix them tomorrow. I have session tomorrow as well. So yeah, we can try to fix them tomorrow as well. Usually the problem is in Python, one common problem is when the version and other thing changes, the code and things, yeah, goes a little bit vary. The code that I tested on my side, maybe older version of Python or something, I don't know. It is working on my side, I tested, and then yeah, if it is not working on your side, there can be several things. One is version problem, and my one installed long ago, and then my machine is a bit older as well, so that's why I need to check where it is going wrong. So today we don't have much time, so we can fix them tomorrow as well, if the time permits. And because it is like 7:10 o'clock, and then there will be quiz. If you do not have like big big questions, or like the questions that I can quickly answer, we could maybe finish. Do you have any like quick question? If you have any quick question. So paper link, you are saying this one, right? This paper. Sorry. This one, right? So if you're referring to this from, so if you're okay, I don't know which one you're referring. This one is that.
Bashar, I think they are asking for Tenogan paper.
Oh, okay.
So what we can do, we can, because we may not be allowed to give them the publisher version.
No, I have the archive version.
Archive version. So that's
Yeah.
where we were thinking, or they can get it through ePrint. So might we give them the ePrint address, so they can, because not everyone have the IEEE access. So might be you can.
But archive is free and open for
Archive
everyone.
is free, or ePrint QUT is also a good way to give.
Yeah. Another option could be QUT ePrint.
Yeah.
Yeah, so yeah, this is another option to do. This is also available publicly.
Yep, so you can obtain from ePrint as well. So yep, so I think now we will wrap up the session. If you have got any burning questions, you can write it in the chat. Otherwise, we'll finish. We'll give you a few minutes break. So as Namita informed, you will have a quiz 3 at 3 p.m. So there are a total of 3 quizzes in this course. One would be this week, another would be next week, and then the last one would be in the last weekend of this session. So now every week you will have 1 quiz on Saturday, and as Namita informed, we will give you the best out of 2 best out of 3. So it's a good idea to attempt all 3. And the quizzes are not really very complex. It's based on what you have learned, so you get enough time. So last weekend, module 1 and 2, so the quizzes is based on that. And now the next quiz would be based on module 3 and 4. And I think there is also a difference, as I said in the beginning of the module 1, that I think we advertised another module for tomorrow, but we have swapped the order. So the next week, Bashar will join again, and would talk about how Gen and other LLMs can be used for information extraction problem. I'm just checking, as Namita said, that joined in, and as Namita said before, that every academy has also teaching assistant. So if you have got any programming issue or any other issues, you can also contact them. And also, as she said, that those TAs are also available physically. So as she was inviting some of you in MNIT last time, so please contact her for more details if you like to have that information. So at this point of time now, we will wrap the session. I think I'll hand over to Bashar to just rephrase what were the main points that he covered in this hands-on session, and something that he wants to add, and then we'll finish soon. So you can have a little bit of break before you could do the quiz at 3 p.m.
Yeah, okay, thank you, Richie. So in this hands-on session, we tried to implement this Tanogan. So we selected this one that it was a simple one to explain how GAN works and how GAN can be used for time series anomaly detection. So initially we explained the Tanogan paper, went to some of the theories, tried to explain from high level instead of going very technical. And then we went to the code, explained the different parts of the code, especially generator, discriminator, and how to train them, what are the tricks there, and so on. And we tested it on CPU machine and shared the GPU version of it as well. So on my end, I ran it again this time, and it was working perfectly. But it looks like for some people it is not working. The reason might be version problem. And then so for that part, if time permits, we can answer some or try to fix some of the problems tomorrow. As Richie mentioned, it is also possible to get help from teaching assistants as well. Yeah, so another thing was that based on your data complexity and things, you can choose GAN and other models. It depends on data complexity, time record time, and so on. Yeah, so yeah, so we'll have a session tomorrow where we'll talk about how to combine this GAN and also how to use language model for information extraction. So that time we'll have a little bit more idea of how things are working and so on. Thanks all for joining.
Yeah, just one last thing I just wanted to add, that sometimes it's a good idea to run the codes in Google Colab, because Google Colab looks after all the version variations and control. So that may be another way you could run this code and try. Okay, so have a great day, and we'll see you tomorrow again for the next module. I hope you have a relaxing tonight, so you join tomorrow again. See you then. Thank you, Bashar. Thanks for the very informative session. And I'll now hand over it to Professor Namita. Thank you, Bashar. Thank you, Namita.
Yeah, thank you, Dr. Bashar. Thank you, Richie. So we are all set for quiz, and it's quite easy. You have done the lectures and sessions before in hand, and it's 1 week before we had done it. We are not covering today's session. It will be covered in the next quiz. So best wishes. We are here to help you in case you need. Please remain joined in here. Thank you, Richie. We'll keep you updating. Thank you.